Hello, welcome to Material Science lecture. So we are going to continue on Module 7 where we're going to look into thermal processing of metals. So we're going to focus our attention on how we can do different type of thermal processing on steel metals. So in the previous lesson you've learned about steel. What is steel and how the solidification of steel happen, the different type of steel. Here we're going to look into how, when the steel is already being solidified, how we can change its behavior, mechanical behavior, by conducting different type of thermal processing, or you might know this as heat treatment. So let's get started. So there are different types of heat treatment that can be conducted into any metals to change its behavior. So in this lesson, we're going to look into several. Specifically, we're going to focus on how we can change the behavior of steel. By the end of this lesson, I hope you will be able to understand a different type of procedure of heat treatment, such as annealing and normalising. You will be able to understand what is quenching and tempering process, and you would be able to understand how heat treatment can affect the mechanical behavior of metals, and in particular in steels. So just a little bit of recap from previous module. In module 4, we have learned that when a metal is plastically deformed by co-working, the metal can become strain hardened, resulting in increase of its strength, but we will sacrifice its ductility. We also learned that this is because the microstructure of the metal is going to be elongate, and it's going to cause this metal to become anisotropic. And also we have learned that this strain hardened effect can be removed by process annealing. So process annealing is a type of heat treatment. So this same process annealing can be conducted in different type of metal to change its behavior after it's being cold worked, and in particular it can be done to steel as well. Also from module 6, we have learned that when alloy being solidified in a rapid cooling rate, what can happen is that our crystal grain will have a microstructure or crystal segregation. So the resulting alloy will have a compositional gradient throughout the grain. And in order for us to remove this effect, we can anneal the materials to make that crystal grain homogenized. So all of these two types of procedure that we did to change the microstructure of the materials is what we call as heat treatment. I'm pretty sure all of us have seen this kind of process being performed to metal before. For example, sometimes we watch a movie, we saw a blacksmith trying to forge a sword or a knife. What he will do is that he will put the metal inside the fire first before he starts hammering it to shape that materials. Also, when they try to sharpen the knife, what they will do is they will heat up the metal first before they start to shape it again. So this kind of process is what we call as heat treatment. What they did is actually they changed the microstructure of the materials so that it can be processed further. So heat treatment is a process of heating and cooling of metal using specific method to obtain desired mechanical properties. So depending on what you want to achieve, you can perform or conduct different type of heat treatment. So let's say you want to have a steel with higher hardness, you can perform quenching and tempering. Or if let's say you want to draw steel, so you want to make their shape smaller and smaller, so you will conduct extensive cold working. So after some percentage of cold working, the metal will be brittle. So what we need to do is to perform a annealing process to change its microstructure so that these materials can become softer again or ductile again. So we perform what we call as process annealing. So depending on what you want to achieve, you can perform or conduct a different type of heat treatment. So in this lesson, we will look into 4 types of heat treatment process, which is annealing, normalizing, quenching, and tempering. And we will focus our attention into steel metal. So for steel metal, the temperature where we will need to heat the metal in different type of heat treatment will be in reference to where the microstructure transform in the phase diagram of iron carbon. So let's begin by annealing heat treatment. So it is a type of heat treatment that will alter the microstructure of metal to change its mechanical and sometimes electrical properties. So this metal, typically such as steel, when we perform annealing process heat treatment, it will reduce the hardness of the metal, and in return we will get the metal with high ductility so that we can process it even further. And also with annealing process, it will help eliminate internal stresses. Internal stresses can be generated by strain hardening effect as well. When we perform core working, what we learn from module 4 is that we introduce a lot more dislocation that will entangle with each other, and this cause internal stresses. So with annealing process, we can reduce or eliminate that effect. So the 3 most common annealing process are full annealing, process annealing, and spheroiding annealing. So these 3 types of annealing process will give you metals that have different mechanical properties. So with full annealing, it is often utilized in steel that will be machined or will experience extensive plastic deformation during forming operation. So forming operations such as bending, rolling, drawing, forging. So if you want to reshape these metals, the steel over and over again, what you can do is that after you shape it, you conduct this heat treatment that we call as full annealing over and over again, and then shape it again. So this heat treatment is performed to produce coarse microstructure which will increase its ductility. So we know that with a microstructure of the grain size, that's bigger grain size, the materials is more ductile. So this full annealing will result in a microstructure of the steel that is much coarser. So in return, you will have a metal that has high ductility. So I will use full annealing process for hypoeutectoid steel as an example. By now, you should be able to state what is hypoeutectoid steel, what is eutectoid steel, and what is hypereutectoid steel. I want you to pause this video and sketch the hypoeutectoid steel microstructure at room temperature. If you don't know how to do this, go back to lesson 1 of module 7, where I have explained about this microstructure. All right, so I hope you do that. You pause the video and sketch it. So by now you should know that the final microstructure of hypoeutectoid steel at room temperature will consist of ferrite and pearlite. I've explained pearlite is a microstructure that consists of cementite and ferrite in a lamellar microstructure. So to conduct full annealing for this type of steel, we have to heat it up above the temperature where austenite starts to form to become pro-eutectoid ferrite. So for hypoeutectoid steel, if you look at the phase diagram, above this line here, everything will transform into austenite. So for hypoeutectoid steel, we said that hypoeutectoid steel lie on the left side of the eutectoid composition. So to transform it back to austenite, we need to heat it up 50 degrees above this line. So for each composition, we heat it up 50 degrees above that AC3 line. So this line we denote it as AC3 line. So during the beginning of this stage where we heat it up, this is the microstructure of the high pore eutectoid steel. So the microstructure at room temperature, when we heat it up, the beginning of the process, we will have this microstructure. So we have perlite and we have ferrite. So this ferrite is pro-eutectoid ferrite. If we soak this microstructure at this temperature, which is 50 degrees above the AC3 line, for a certain time, we soak it for a length of time, everything will transform back into austenite. So this process is what we call as austenization. So we soak it, we hold it at that temperature for a period of time. All of this microstructure will transform back to austenite. And then the next step, what we need to do for this heat treatment is that we need to slow cool it. So in order for us to slow cool these materials, for full annealing, it needs to be done in a slow cooling rate. So for us to do this is just to cool it inside that furnace. So it will take a longer time to cool it rather than if you take it out. So during this slow cooling process, we will allow diffusions of hard atoms to happen. So grain growth will happen at the end during this process. At the end, you will have a microstructure that have a grain size larger than when it begins. So we're still going to, at room temperature, we will still have ferrite, pro-eutectoid ferrite, and perlite. But now the grain size is much bigger because of the diffusions of atoms, the grain growth process. So that is how full annealing process for hypoeutectoid steel being performed. For hypereutectoid steel, in contrast with the hypoeutectoid steel, for hypereutectoid steel, we cannot perform full austenization. We cannot use this line. Instead, we have to heat it up above this line here. So this line is what we call as AC1 line. So we heat it up above this line. So some of the microstructure will turn into austenite, but the cementite, the pro-eutectoid cementite, will still be there. And the next step, we will need to slow cool it in the furnace again, in which the austenite will slowly transform, but with a bigger grain size. So that's how full annealing for hypereutectoid steel being performed. So just a little bit more information on austenizing. So during this process, what we call as austenizing, the BCC ferrite will start to transform back into FCC austenite. So for full annealing, for hypoeutectoid steel, so I'm talking about hypoeutectoid steel, what I said before is that we need to heat it up above this line here. So when we heat up above that line, hold it for a period of time, all of the microstructure will transform into austenite. For hypereutectoid steel, in full annealing, we don't have to do this. But in another heat treatment that we call as normalising, we will need to do the same thing. So in order for us to transform everything back into austenite for hypereutectoid steel, we need to heat it up above this line here. So this line is what we denote as ACM line. So during this process, the BCC ferrite will transform into FCC austenite. So if, let's say, we look at the microstructure of the hypoeutectoid steel, what happened during austenizing process is that the cementite from the perlite will start to disintegrate upon heating, and then the pro-eutectoid phase, which is here is the ferrite, will also transform into austenite. So the final microstructure that you will get during this heating process is austenite. So the second type of annealing process that I will discuss is what we call as process annealing. So we have already looked into this process in module 4. So process annealing, or sometimes we call it as stress relief heat treatment, is a heat treatment process that is used to remove the effect of cold working. So the strain hardening effect. So for steel, this treatment is usually only applied to hypoeutectoid steel with a composition of carbon of less than 0.3 weight percentage. So it is carried out at a temperature below the eutectoid temperature, usually between 550 degrees Celsius and 650 degrees Celsius. So no transformation of phases happen. So this process is done below the eutectoid temperature. So you will still have the microstructure of pro-eutectoid ferrite and perlite. So let's have a look at how process annealing for hypoeutectoid steel being performed. So for hypoeutectoid steel, as I said, we want to avoid any phase transformation to happen. So phase transformation will start to happen at eutectoid temperature. So we will heat up. The first step is to heat up the materials, the metal, which in this case hypoeutectoid steel, below that line there. So around, let's say 650 degrees Celsius, you won't have any phase transformation. No alpha ferrite can transform into austenite, no matter how long you hold it at that temperature. So we want to avoid phase transformation. So this line here is what we denote as AC1 line. So that's the first step, is heating the metal below AC1 line. So initial microstructure for this steel will have a highly deformed microstructure because we already processed them. So we will have a microstructure that is elongated in the direction of the cold working. So this microstructure, we want to avoid this microstructure because it is very unpredictable and it's anisotropic microstructure. So we want to return it back to equax microstructure. So we heat it up to a temperature below that line and soak it, hold it for a certain period of time where we will allow recovery to happen, recrystallization to happen during this process. Recovery and recrystallization I have already explained in module 4. So go back to module 4 if you don't understand. So during that process, this microstructure will transform into equax microstructure. So this microstructure is actually the initial microstructure before co-working being performed to these materials. So with this grain refinement, with this heat treatment, grain refinement is produced without any phase transformation. So you can see that in the beginning you have alpha phase, you will have ferrite phase, and you will have cementite here in the microstructure of perlite. So in the perlite you will have cementite, Fe3C, and ferrite. So you have two phase. During this process, no phase will be transformed into austenite. At the final hour or minutes or second that you have finished this second procedure, you still have the same phase, which is ferrite and cementite, but now the microstructure shape just going to look different. So during this, after this process, if you slow cool it inside the furnace, you will allow diffusions of atoms to keep going, so that the final microstructure that you will obtain is a microstructure of equivalent microstructure with a bigger size. And therefore this metal will be much more ductile, so you can process it again. However, if let's say you want to retain this microstructure, the small microstructure, you want to retain this, because we said that materials with a smaller size grain is much stronger. If let's say after this soaking process you want to retain this, you can do that as well. What you need to do is just to quench it to room temperature straight away. How did you do that? Take it out from the furnace and put it inside the water straight away. So during the first slide where I show you the clip, that's what they did. They want to retain that microstructure, which will give a higher strength. What they did is that they take it out and put it inside the water straight away. So the temperature will transform to room temperature in a rapid cooling rate. So apart from the first two annealing process, which is full annealing and process annealing, we also have another type of annealing process that we call as spheroidizing annealing. So this heat treatment is performed to convert lamella cementite into spheroidized structure. So during the solidification of steel, we know that at room temperature, we will have some portion of the microstructure, or if not for eutectoid steel, we will have all of them in the lamella microstructure. So we will have ferrite and also cementite in the layered cake microstructure. So we can also perform an annealing process that we call as spheroiding to convert this microstructure of cementite to become sphere like this. So this is also cementite, but it is in this form here. So spheroidized steel have a maximum softness and ductility and are easily machined or deformed. So this is why we conduct this heat treatment. So as you can already predict by now, I hope, this microstructure will be harder than this microstructure. So we want to be able to easily machine these materials. What we need to do is we conduct this heat treatment that we call as spheroidizing, and this will conduct the stripped cementite into spheroidized cementite. So this heat treatment process begins by heating just below the eutectoid line at 700 degrees Celsius. So the eutectoid line is 727 degrees Celsius. So at this temperature, phase transformation will start to happen. So we want to avoid this. We will heat it up at 700 degrees Celsius. The difference between this and process annealing is that it will be conducted, it will be soaked at this temperature for a much longer time to allow the cementite in the perlite, which is in the strip form, to transform into spheroidal cementite. So it will require a much longer soaking time, between 15 to 25 hours. And after that, the materials again for annealing, it's always going to be conducted in slow cooling. So after soaking for 15 to 25 hours, the steel will be slow cool inside the furnace. Now let's move on to normalizing. So normalizing is a heat treatment process in which the steel is austenized and then air cooled. So in contrast with annealing, annealing process, always the cooling process is done inside the furnace. However, with normalizing, we take out specimen from the furnace and we let it cool at room temperature, at ambient temperature. So you can imagine that the cooling rate is now much faster. So there are different purposes why heat treatment, this type of heat treatment is being done, and some of these are to refine the grain structure, to increase the strength of the steel compared to anneal steel, and also to reduce microstructure segregation. So annealing process can also be done to reduce microstructure crystal segregation, same as normalizing as well. Let's have a look on how this heat treatment process being conducted to hypoeutectoid steel. So let's say, for example, you have a steel, you know the composition is hypoeutectoid steel, and you look under the microscope, what you can see is the grain size are not the same all over. Some of them are bigger, some of them are smaller, some of them a longer, so it is a heterogeneous microstructure. The size are not the same. So as we know that we want to avoid this, so you can conduct normalizing heat treatment to change this to the same size all over the volume. So what you need to do for hypoeutectoid steel is to heat up the materials above this line here, above the austenite transformation line. So you take that steel that you have in your hand and you heat them up 55 degrees above the temperature of that, above the AC3 line. So let's say you have 0.4. This is where the temperature where the ferrite and cementite, all of them are going to change to austenite. So you heat it up 55 degrees above that point there. So this is the microstructure that you have observed. You want to transform them. After soaking it for a certain period of time, all of these phases will transform. The ferrite and cementite will transform into austenite. If you allow this to cool at room temperature for a certain period of time, the austenite will transform again to ferrite and perlite, but with a homogeneous microstructure. So that's how we conduct normalizing heat treatment. And for hypereutectoid steel, what we need to do is to heat up above this line, 55 degrees above this line. So you will transform all the cementite and ferrite for hypereutectoid steel if you heat them up above this line here. So different composition, you will need to heat it up at different temperature. And finally, let's have a look into quenching and tempering. So this is a two-stage heat treatment process. So it's always with the aim to strengthen or to harden steel. So it's not for processing anymore. It's to get the final microstructure. Either we want it to be stronger or if we want it to be much harder. So the first stage always involves heating up the steel above the austenite transformation line. So here, if you look at the phase diagram for hypoeutectoid steel, it will be heated up above this line. For hypereutectoid steel, it will be heated up above this line here. I know you might be asking, the microstructure won't be transformed to fully austenite if you heat up above this line, only above this line. Yes, you're correct, but that's how you conduct it for hypereutectoid steel. This is to avoid a large grain of austenite to be transformed. So if you heat up above this line, you will allow a lot more diffusions of atoms to happen. So your grain size of austenite here will be much bigger. So we don't want that. So what we did instead, we just transformed the ferrite into austenite at temperature above this line. So your microstructure at this point will consist proeutectoid cementite and also austenite. So that's how the hypoeutectoid austenization process will be done for this type of heat treatment process. And after that, after austenizing, we will perform quenching process for this heat treatment. So quenching is when we quench the material straight from that austenite phase to room temperature without diffusions of atom allowed to be happen. So what we will need to do is to quench it from, let's say, 900 degrees Celsius for this type of materials, this composition. So we heat it up to this temperature, 880 degrees Celsius. So as soon as we get to transform them all to austenite, we quench it straight away to room temperature. So how do we do that? We can straight away rapidly put it inside the water or oil or air. So that's like a different quenching medium. So the temperature will change drastically. So this is a diffusionless process. And the second step is what we call as tempering. So depending on what you want to achieve, you can temper them to a different temperature. So tempering process is done by heating the materials below austenizing temperature. So we heat it up again in the second step. So depending on what we want to achieve, we can temper at different temperature. So that is tempering process. Quenching process is the rapid cooling of metal after austenizing using different quenching medium. So the most popular quenching medium is water, oil, air, and also brine. Brine is a mixture of air with salt. So during using different quenching medium, the rapid cooling rate will be different again. So what we need to do during this quenching process is we take out the steel from the furnace and dump it inside this different type of quenching medium, and it will allow it to cool at a very rapid cool. So in this process, phase transformation at lower temperature do not occur. So what we have learned before, for steel, when solidification happens, phase will start to transform from liquid to austenite at certain temperature. As the temperature drops, what will happen again, slowly, as the temperature drops slowly, austenite will transform into cementite and ferrite. But with rapid cooling, we will prevent that cementite and ferrite transformation from happening. Instead, we will create another type of phase, which we call as martensite, and I will explain this in the next slide. So in general, for metal, quenching can reduce the crystal grain of materials to increase the strength and hardness. Specifically for steel, this process is mainly applied to harden the steel. So what happened during steel quenching? So at room temperature, if we have a already solidified steel, we will have a steel that consists of ferrite and cementite phase. Okay, and then we perform heat treatment in which we heat these materials to decompose these two phases to become austenite again. So we heat it up, everything will transform into austenite again. So we know that austenite has a carbon atom, a crystal structure with carbon atom residing inside the FCC unit cell, as what you can see here. So you can imagine inside this middle interstitial, we have carbon atom. This carbon atom here belong to the unit cell in front of this unit cell that you can see here. So you have the carbon atom residing inside the middle interstitials of the FCC crystal structure. So this is austenite. So if we allow it to cool slowly again, what will happen? This austenite will transform into ferrite, and the carbon atom will diffuse out. So what you get is a pure carbon atom, a pure iron atoms in the BCC crystal structure. So this is when you slow cooling it. However, if we rapid cool it, the austenite, the FCC transformation to BCC transformation, what will happen is that the atoms of carbon will not have time to diffuse out of the crystal structure. What will happen instead, it will trap inside the BCC crystal structure and it will expand the lattice parameter of that unit cell. So the BCC crystal structure now will have a longer, an expanded lattice parameter with carbon atom trapped inside it. So this is what we call as martensite phase. So it has a BCT, body-centered tetragonal unit cell with carbon atom diffused inside it. And as you can predict already, this martensite did not have slip plane. So there's no plane where dislocation can happen. So this phase will be much brittle and much harder if we compare to these two phases. So this is the schematic of the steel quench microstructure with martensite forming a needle-shaped microstructure or a needle-shaped grain. Not only they don't have the slip plane that allow dislocation to move, they're also going to form a very, very small grain size. So if you look at the hypoeutectoid steel microstructure that has been quenched, this is how it would look like. So from module 4, where we learn about strengthening mechanism of materials, we can increase strength and hardness by transforming the grain size to a much smaller grain size. So this is what happened. This is why quenched steel microstructure is hard and very, very strong. However, they are also going to be very brittle. So this brittleness is caused by the pure martensite, which has no slip plane, and also because of the small grain size that is formed during rapid cooling. So you actually strengthen this material, but at the same time, we reduce its ductility. Also, steel contains fewer carbon atoms than its unit cell. Only some of the BCC cell will expand tetragonally. The others will remain in BCC. So due to the amount of carbon being added to produce steel. So we know that steel only contains 2% or below amount of carbon. So you can imagine in the austenite form, not all of the unit cell of the FCC contain carbon in the middle. Some will not have carbon. So when rapid transformation, cooling transformation happen, some of them will transform into BCT, into martensite. Some will remain into and will transform into ferrite. So you can imagine that the crystal structure will be distorted. So due to these qualities, dislocation throughout the steel will have its motion obstructed. So the produced steel after quenching will be too brittle for any useful application. So as you can see in this microstructure here, nucleation of crack in the steel with martensite microstructure happen. So we basically cannot use them at all. So that is where the second step, which is tempering, will make a lot of difference. So the second step of this heat treatment is the one that we call as tempering. So tempering is a treatment of reheating the quenched steel to reduce its brittleness and increase its toughness. So the heating will be done below eutectoid temperature to prevent austenite transformation. So you will still have martensite. You won't transform it back to austenite. However, during this process of tempering, this martensite will be softened by some of the carbon atom in the BCT crystal structure diffuse out and form cementite and ferrite. Some will still remain in martensite, but some will transform into cementite and ferrite. So you will have a microstructure that is softer than pure martensite. So your strength of the materials will be reduced, however, it will be more useful. It will not be too brittle. So reheating quenched steel will allow diffusions of interstitially trapped carbon and reduce the lattice distortion. So as you can see here, this is the microstructure of the same steel, the one that I showed you just after the quenching before. However, this steel now has gone through both steps. It has gone through quenching and also tempering. Just by looking at this microstructure, we know that it will be much softer and tougher if we compare to the previous one where only quenching has been performed. So this results in a softer and tougher steel. So this is more useful for engineering application. So tempering temperature can affect the mechanical behavior of steel. So if you look at this chart here, with higher tempering temperature and longer tempering time, it will produce steel with higher toughness. So the martensite, a lot more martensite will transform into cementite and also perlite. So the microstructure will be softer and it will be tougher. If we have a lower tempering temperature, it will retain a lot more martensite. Therefore, the steel will be harder if we compare to the higher tempering temperature steel. So this will result in materials with higher wear resistance because the surface will be harder. So those are the different type of heat treatments that can be done to change the mechanical behavior of steels. So in summary, in simple term, heat treatment is the process of heating the metal, holding it at that temperature and then cooling it back. So during the process, the high temperature will alter the microstructure of the metal, and as we know, the microstructure plays an important role in mechanical behavior of a material. So the final outcome of heat treatment process depends on many different factors, which include the heat treatment temperature, the time of keeping the metal parts at a certain temperature, and the rate of cooling. And all of this will affect the final microstructure after the heat treatment. And as we have learned, when we have different microstructure, even with different grain, different grain size or different shape of the grain, it will affect the final mechanical behavior of that metals. So depending on what we want to do, what we want to proceed after that, we can choose different type of heat treatments. So for heat treatment of steel, I can actually characterize them into 3 different cooling rates. So slow cooling rate, so heat treatment like annealing and normalising can be categorized as slow cooling rate. And then we have rapid cooling, which is quenching. And in the next lecture, we will look into moderate cooling rate. And depending on this cooling rate, we will produce different type of microstructure. So with annealing and normalising, we will always get perlite and pro-eutectoid phase. So if for hypo-eutectoid, we will have pro-eutectoid ferrite and perlite. For hyper-eutectoid, we will have perlite and pro-eutectoid cementite. Whereas for quenching, we will always going to get martensite. For moderate cooling, we will have another type of microstructure, which what we call as barenite. And I will talk about barenite in our next lesson. And for martensite, since it's not useful, we need to do tempering process, which will result in what we call as tempered martensite. So this microstructure, the one that I showed you before, is what we call as tempered martensite. So in general, the microstructure the strength of these materials increase from spheroidite to martensite microstructure. However, the ductility from martensite to spheroidite is going to be, the ductility will increase as it goes from martensite to tempered martensite to benite, fine perlite, coarse perlite, and spheroidite. So don't worry, you might not have. I haven't discussed about fine perlite, coarse perlite. I will talk about it in the next lesson. So that's about it for a general knowledge on the heat treatment process for steel. So I hope this lecture has bring you a new insight on heat treatment process and how we can change microstructure of steel, of any metals, but in particular with steel because we use them a lot in mechanical engineering application. So I hope this lecture has give you some insight on how you can conduct this heat treatment to change the microstructure, which in turn will change the mechanical properties of these metals. Thank you very much. I'll see you in the next video.